series is an infinite polynomial in the form shown here. Essentially, all this represents is we have a number of coefficients represented by c sub 0, which would be my constant coefficient, c sub 1, c sub 2, so on. And we can have various rules for calculating those coefficients depending on the type of power series we're dealing with. And then each term has a power of the binomial x minus a. These coefficients, c, the c values are real numbers, and the value of a is a real number, and x represents a real variable. And we would say that this particular power series is centered at a. We can choose to have a polynomial centered at 0, in which case we're going to have just powers of x instead of powers of a binomial. But we choose our a values carefully because essentially we can use these power series to use polynomial approximations of non-polynomial functions. So I can choose a power series to represent a function that is not actually polynomial to make working with that function a little bit easier. The idea being that this power series can converge and therefore look more like it converge to the non-polynomial function around a. So the convergence will depend on the value of a. It will always converge for a. So when x equals a, the series just is the constant term that we have here, CO. So that will always converge. And in this case, we would say if that's the only value where it converges, the interval of convergence is just a to a, or no, sorry. Yeah, interval of convergence is a to a. And we have a radius of convergence of 0 because the interval is basically just that one value when x equals a. Some power series will converge for all real values. So in other words, it is possible to have a polynomial series that perfectly matches the function that we're trying to match. And then our radius of convergence is basically infinite because all real numbers will work. But what's more likely to happen is that we will have a convergence interval that is symmetrical around x equals a. So it would converge for all values of x in the interval a minus r to a plus r, where r represents the radius of convergence. Now, I've written this with closed bounds, but one or both of the boundaries could also be open bounds. So you could have something that looks like a minus r, a plus r, where they're both open, or one of them might be open and one of them might be closed. We'll see an example of that in a moment. But the idea here is that if then I'm wanting to use a polynomial to represent a non-polynomial function, it's unlikely in most cases that a polynomial will perfectly match that function. If I'm wanting to work with the function around the values where x equals, say, 7, then I'm going to want my power series to center at 7 because the fit is going to be best closer to 7 relative to other things. So let's look at an example. This particular power series is centered at 0, which is why we're not seeing x minus a, we're just seeing x, x squared, x cubed, and so on. And just as an example, this one does converge for all values in the interval from -1 to 1, where it does converge for -1 and it doesn't converge for 1. So essentially what I'm saying here, it obviously converges for 0 because it's centered at 0. So this interval is going to be symmetrical. And if I think of values of x that are between -1 and 1, but not 0, let's say x is 1/2. If x equals 1/2, then what this series represents is 1 plus 1/4, because that's 1/2 divided by 2, plus 1/2 squared divided by 3, which is 1/12, plus 1/2 cubed divided by 4, which is 1/32, and so on and so on and so on. This series, this infinite series, does converge. Now, the proof of how it converges is beyond the scope of this course, but it does in fact converge, and therefore this is in the convergence interval. Now, at the boundaries, at -1 and 1, for -1 it does converge. So let's look at what that series is. If x equals -1, then what we have is 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, and so on. This does converge. This is what's called the alternating harmonic series. The proof of its convergence, again, is beyond the scope of this course, but it does converge. Whereas if x equals 1, what gets created is just the harmonic series. 1 plus 1/2 plus 1/3 plus 1/4, and so on. And when the harmonic series is not alternating, it actually diverges. Again, proof is beyond this course, but one boundary can converge and the other doesn't necessarily converge. Any x values beyond that are somewhat trivially going to be non-convergent. So let's say I said x equaled 3. If x equals 3, then I have a numerator that is bigger than the denominator as my terms go on. So I have 1 plus 3 halves plus 9 thirds plus 27 quarters and so on. Obviously, the thing that I'm adding each time gets larger. So this will have to diverge. And just to complete this first one did converge. Determining convergence divergence is a non-trivial topic, so I'm not going to get into that too much right here because it's actually quite complicated. There's a number of tests to determine if series converge or not. Now let's consider this next polynomial. So this series is centered at 1, and again, we've got a rule here for how we're calculating that infinite polynomial. Our values here are starting at 5 instead of 1, so our first term actually already is the 10th power. We don't have any powers less than that, and we end up only having even powers of the variable. This one just happens to converge for all values between -2 and 4. So again, that is symmetrical around 1, because this is essentially 1 minus 3, 1 plus 3. So the radius of convergence in this case is 3. In the previous case, the radius of convergence was 1. It's a little easier to determine the radius of convergence when we're centered at 0, but still not super hard. Thinking about what that looks like for values inside of that interval. So for example, if x was equal, let's say x equals 0, so that's going to be a relatively easy one to calculate. What we get then is 1 over 9 to the power of 5 plus 1 over 9 to the power of 6. If x equals 0, each of our numerators is just going to end up being 1, because while 0 minus 1 is -1, we only have even powers. And as I'm adding these terms that are vanishingly small, this does actually converge. Whereas if I consider something outside of that interval, so let's say, for example, x equals 5, then what I see in that case is 4 to the power of 10 over 9 to the power of 5, plus 4 to the power of 12 over 9 to the power of 6, plus 4 to the power of 14 over 9 to the power of 7. Our numerators are growing quite rapidly relative to our denominators. That does diverge. And in this particular case, neither of the boundaries will converge or diverge, which if I consider what happens at one of those boundaries, so let's say where x equals 4, when x equals 4, x minus 1 is 3. 3 to the power of 10 is the same as 9 to the power of 5. And 3 to the power of 12 is the same as 9 over to the power of 6. And so on. So this one is a little more obvious to see why that is going to diverge, because it's just 1 plus 1 plus 1 plus 1 infinitely, which is clearly going to diverge. And the same thing will actually happen for -2, because -2 minus 1 is -3. -3 to the power of 10 is equivalent to 9 to the power of 5, and so on.